We've been talking a lot about work and potential energy and saying things like change in potential energy is the same thing as the negative work done for an internal interaction. Okay, so not external, but if we're considering it to be a potential energy, it must be inside the system, and we're thinking of it as the work done between the two, or the one object on the other, which are both in the system. So we've thought about it this way. And then we've talked about potential energy then being related to forces. Now we have to put a caveat on that of when we can think of it this way. When we can actually consider an interaction to be internal work and therefore equal to a change of potential energy. And that is if the work done is path independent. Okay, now what does that mean? So if I take an object and I apply a number of forces to it, or a force, in such a way that this object goes like this and ends up over here. Okay, well that's a path, that's some delta S1, and if I apply some force on it over that delta S, along that S, I'm going to get a work done. I'm going to get some amount of work done, some W1. Okay, well what if I do it again, applying that force over a different path, but I end up at the same spot. So these are two different paths. So we have now a delta S2, and I apply that force on it, Fs. That's going to give me a work 2. The paths are different. The forces are they could be different. They could be the same, but the works could be the same or could be different. It just depends on how this force operates along those two paths. Okay. Now, for example, if this was a vertical change in position, so this is y, and I asked the force done by gravity as the object moves from here to here, we've seen before that it doesn't matter if it goes this way or goes this way, because the only thing that matters is the change in height. Okay? Because gravitational force always points straight down, always points straight down. And so you can do all your components here, and you can figure out that it doesn't matter which path. You can go straight there, you can go straight over, and then straight up. It really doesn't matter how you go with the force of gravity. You'll end up with the same work done. And therefore, we can say, also consider it to be a potential energy. But, having said that, there are many forces in reality that we see every day that are not do not follow this. Meaning, if I go one path versus another, I will get a different value of work done depending on the path I take. Okay, so friction's an example of one of these, which we've already kind of said that it's special, and so we call it a delta E thermal, or it causes a delta E thermal. But for this particular case, it would be different based on the path I take. It'd be bigger for a longer path. And then other ones are just like pulls and pushes. You know, if I'm pulling in one direction and get between two locations, then I will have a different work done depending on what type of force I'm pulling. Now, some forces work out. For example, you know, some constant forces that are in the same direction as the path, they would actually work out and get the final answer. But just to be complete and clear, there are many forces that are what we call non-conservative. And that's because we can't convert them into an internal work and therefore call it a change of potential energy. Because potential energy in the mechanical energy, where we say the K initial plus U initial would equal K final plus U final, it's not conserved. Those two quantities aren't conserved. Because if the work changes based on path, well, these quantities all depend on endpoints, just where you're at, not how you got there, just where you're at. Thankfully, even though that is an issue, thankfully, there are many forces that we deal with: spring forces, elastic forces, gravitational forces, and we're going to find future electrical forces, which are a large portion of forces, just not all the forces we deal with. But those are path independent, so it doesn't matter which path I take. And therefore, they are conservative forces because I can change the work done by those forces excuse me, into a potential energy and therefore conserve mechanical energy. So that is what a conservative force versus a non-conservative. Just think about path dependence. A non-conservative force depends on the path. A conservative force is path independent, and therefore we can write the work done by that force as a potential energy inside the system.